hey there, this is Chris Clements here with a final podcast for this school year. This one is going to be on nuclear chemistry. Okay, let's go ahead and get started. So, when we talk about nuclear chemistry, we're talking about nuclei, meaning the small part of an atom. So let's start with who did what. Wilhelm Röntgen was a gentleman who generated phosphorescence, meaning glowing, in a laboratory from unnatural source. He named this unnatural source of phosphorescence as X-rays. So once he discovered X-rays, a gentleman named Henri Becquerel, French gentleman who was, I believe, a second or third generation scientist in his family, had inherited some uranium salts or ores known as pitchblende. He happened to notice after setting the ores on photographic paper that the photographic paper seemed to have been exposed to light. So in essence, with repeated trials of that sort, he discovered natural phosphorescence. It was known for quite a long time as Becquerel phosphorescence, and it is known as spontaneous phosphorescence as well. Two folks, Marie and Pierre Curie, studied Becquerel phosphorescence and renamed it radioactivity. Marie was Polish, Pierre was French. They together did an awful lot of work in the field of nuclear chemistry. They're responsible for having discovered polonium, an element that has radioactive isotopes named for her homeland in Poland, and radium, an element with radioactive isotopes named for the fact that it radiates light. A little bit of review before we get into nuclear reactions is remembering how to write an isotope's formula. If you recall, you write the formula of an isotope as the elemental symbol supported by a superscript to the left and a subscript to the left. The superscript to the left in nuclear terms is generally represented as A, and the subscript to the left is generally represented as Z. The A, or superscript to the left, is the mass number. It's the sum of the number of protons and neutrons. Z, the subscript to the left, is the atomic number. It's the number of protons. In an atom, it can also be the number of electrons, but again, we're speaking of nuclei here, so we're focusing upon neutrons and protons. And we can determine the number of neutrons if we subtract Z from A. In other words, atomic number subtracted from mass number gives us the number of neutrons. Radiation exists due to an instability that is present in the nuclei. That instability is due to the ratio of neutrons to protons. Any elements who have instability due to neutron and proton ratio is known as a radioisotope, and its whole goal in its existence is to reach stability, so that radioisotope will go through certain processes to become more stable. If you look at the slide associated with this, it is known as a zone of stability diagram. That zone of stability shows us that as atomic number increases on our x-axis, the neutron number for stable nuclei should also increase. That ratio is 1 to 1, neutron to proton ratio, for elements atomic number 1 to 20. As the atomic number increases, that ratio can increase as well. If you look at the example, cadmium 140 has a 1.29 to 1 ratio. Mercury 202 has a 1.53 to 1 ratio, and so on and so on. And you notice just above Mercury, we don't have any red dots anymore. The red dots symbolize the naturally occurring isotopes, those that are stable. The blue dots represent the naturally occurring, or in some cases, synthetic isotopes that are unstable and will undergo some form of radiation, meaning radiating energy or light, to become more stable. As you go beyond Mercury and you see that there are a few more elements with red dots, we get to a point where there are no red dots, and what that means is we just don't have any isotopes that are stable. So there are some elements with isotopes that just are not stable. Typically above atomic number 83, we do not find stability. Ernest Rutherford was a gentleman who did the gold foil experiment that you may recall, where he fired what we called alpha particles at gold foil to prove that the nuclei were really non-existent, since we didn't know anything about nuclei at that point. What he actually did was prove that nuclei did exist. He disproved the plum pudding model. He was able to establish an electric field surrounding radioactivity, and in doing so, he isolated 3 types of radiation. So I'm going to go over in great detail these 3 types of radiation, alpha, beta, and gamma, and then give you a few more types of radiation. We'll work on writing some nuclear equations while we're at it. Alpha particles, he discerned, had 2 positive charge and would be attracted to a negative plate that he had set up, as you see in this diagram. Beta particles had a 1 negative charge and would be attracted to the positive plate, as you see in this diagram. The beta particles with lesser mass ended up being able to be deflected more, so you see that their curvature is a little bit greater. Gamma rays had no charge, therefore they were not deflected. So let's go into a little deeper detail on alpha radiation. It's written with the Greek letter alpha. An alpha particle is the same thing as a helium-4 nucleus. That 4 in the name helium-4 nucleus is the mass number of helium. It would be written again as a superscript to the left. Its atomic number, which you find on the periodic table as 2, would be written as a subscript to the left. Every time an alpha particle is emitted by a radioisotope, the mass number decreases by 4 and the atomic number decreases by 2. And I've shown you as an example reaction that radium-226, which has an atomic number of 88, emits an alpha particle. So you see the alpha particle represented on the product side. The way to figure out the other particle is just to make the sum of mass numbers on the left equal the sum of mass numbers on the right, and make the sum of atomic numbers on the left equal the sum of atomic numbers on the right. So when we do so, if I acted like the other isotope were not present, and I subtracted 4 from 226, I would get 222 as my missing mass number. If I subtract 2 from 88, I get 86 as my missing atomic number. I then look on a periodic table to see what element with atomic number 86 is, and I see that it is radon. So my missing particle is radon-222. If radon-222 were deemed unstable, it would go through another decay, perhaps emitting an alpha particle or perhaps another type of particle. Alpha particles are not very penetrating. They can be stopped by a sheet of paper, yet they are very ionizing. That means they tend to encounter an atom and either steal an electron from it or give it an electron. So we tend to say in medical terms that ionizing radiation causes free radical development. You've probably heard of ultraviolet radiation developing free radicals. Well, it's the same kind of concept. We're talking about energy here. Second type of radiation is beta radiation, written with the Greek letter beta. It's the same thing as an electron, yet we don't write it as we did in redox reactions. We write a lowercase e and give it a mass number of 0 and an atomic number of -1, indicating that its mass is so small it's negligible and that it does not have any protons. In fact, it has a charge of -1 or 1 negative, however you wish to represent that, but typically written as -1. Every time a beta particle is emitted by a radioisotope, the mass number remains the same, but the atomic number will increase by 1. So I've given you as an example iodine-131. Iodine's atomic number is 53. If I do indeed tell you that it is a beta particle emitter, then you know that it will emit an electron, which we write as lowercase e, mass number of 0, atomic number of -1. When I make sure that my mass numbers and atomic numbers sums equal each other on left and right side, I find that the missing mass number is 131 and the missing atomic number is 54. When I look on a periodic table, I see that element with atomic number 54 is xenon. Thus, xenon-131 is the product in this particular decay. Beta particles are more penetrating than alpha particles. It takes a thin sheet of metal to stop them, yet they are less ionizing than alpha particles. The third type of radiation that Rutherford discovered were gamma rays. They're not considered particles, though in some cases folks do consider them to be particles. They are considered to be pure energy. It usually accompanies alpha and beta radiation. It is more penetrating than alpha and beta radiation. It is somewhat blocked by several inches of lead or several feet of concrete. If you've ever had an X-ray and they've put a lead apron on you, that's explaining to you that X-rays are stopped by just a few millimeters of lead. If you had an apron of several inches of lead laid upon you, you would be very uncomfortable. And gamma rays are less ionizing than both alpha and beta particles. So when I show you an example of a gamma ray equation, I tell you uranium-238 emits an alpha particle and gamma rays. You see that we did the same sort of thing with the alpha particle, wrote helium-42 as we had done earlier, but we write gamma-00. It has no mass and it has no charge, and there are two there because two rays are detected. The other product is thorium-234. All that change in mass number and atomic number comes from the alpha particle strictly. So every time a gamma ray is emitted, there is no change in atomic number, nor is there a change in mass number. Two other types of radiation that I'll discuss are the positron, which is simply a positively charged electron. So it can be written as the beta symbol, the Greek letter beta with a plus sign, as its charge per se. It has the same mass as an electron, but it has an opposite charge of an electron. Fluorine-18 is a positron emitter. So when I write it, I write E, 0 as its mass number, positive 1 as its proton number or atomic number. Thus, the mass of the radioisotope fluorine-18 will not change, but its atomic number will decrease by 1 so that we get oxygen-18 as our product. If you click on the box that pops up in the actual PowerPoint, you'll get a little movie on PET scanning. PET scanning is called positron emission tomography, and it uses the radioisotope fluorine-18 tagged onto a glucose molecule that emits positrons, which when they encounter electrons, it's matter encountering antimatter, it emits energy. That energy that they emit when they annihilate each other is detected, and it's able to form an image, because substances that are big users of sugar will take up this sugar molecule that's radioactively labeled with the fluorine-18. For example, a cancerous tumor, cancer cells love to replicate, therefore they need lots of sugar. So they would take in a fluorine-18 molecule very voraciously and show lots of signaling that energy was around it. So it's a good way to image cancerous tumors. So once you've finished watching that, you certainly may continue this, or if you just want to go back to it later, it's kind of a cute little short movie. All right, the other type of radiation that I'd like to discuss with you is the opposite of beta emission. It's electron capture. So rather than emitting an electron, some radioisotopes will take in an extra electron. Now, I keep mentioning this electron business. The whole root of this, remember, is nuclei. We don't have electrons in the nucleus, right? Well, you should recall that a neutron is actually a proton and an electron that are fused. So if a radioisotope is going through beta emission, kicking out an electron, then it takes a neutron and breaks it up, kicks out the electron, and takes on essentially another proton, which is why the proton number goes up. If it's capturing an electron, it means that it's going to take a proton, bond it with the electron that it's captured, and make a neutron. It is the exact opposite of beta emission. The mass number will remain the same, but the proton number or atomic number will decrease by 1. Potassium-40 is a capture of electrons. So when I write its reaction, again, I just have to make sure the mass number on the left equals the mass number on the right. So my new substance will have a mass number of 40, but its atomic number will be 18, and that is argon-40. A decay series occurs when a radioisotope decays into something that is unstable, and so it decays into something that is unstable, and so on and so on and so on until something stable is reached. So I'm going to give you as an example francium-221. It undergoes the following decay series. It emits an alpha particle. In a second step, it emits another alpha particle. In a third step, it emits another alpha particle. In a fourth step, it emits a beta particle. In a fifth step, it emits another beta particle. And finally, when it emits that sixth time as an alpha particle, it reaches something stable. So all you're going to do is write 6 nuclear decay reactions. We start with francium-221. You look up on a periodic table, francium's atomic number is 87. It kicks out an alpha particle, so a helium-42 nucleus. Again, just make sure your sums equal on left and right side for mass number and atomic number, and you'll find that you have astatine-217. Well, because we go through another decay, that's telling us that astatine-217 is not stable either. So I then take astatine-217 and make it emit an alpha particle. When it emits an alpha particle, again balancing my mass number and atomic number, I will have bismuth-213 produced. And again, we just keep going through this. Bismuth-213 is unstable, so it emits another alpha particle, and it forms thallium-209. Thallium-209 is not stable enough, but it will emit a beta particle, which you recall is an electron. So as it emits a beta particle, it forms lead-209. Lead-209 is not stable enough to exist, so it emits another beta particle and forms bismuth-209. We're back at bismuth again. Yep, bismuth-209, however, goes through alpha decay and finally produces thallium-205. Thallium-205 is a stable isotope. It is not considered a radioisotope. So that means francium-221 undergoes that decay series and finally ends up being thallium-205. Every one of those reactions has a certain amount of time that it takes, and that time that it takes indicates essentially how dangerous the substance is. The longer it takes to go through that decay, the safer the substance is, because it's not emitting the energy just instantaneously. What I'd like to go over now is the rate of radioactive decay. In doing so, we need to look at two things: half-life and the kinetics of radioactive decay. Half-life is defined as the time that it takes for half of a substance to disappear. It's not really disappearing, it's just going through decay. So it's the time it takes for half of a substance to decay into another substance. We determine half-life by taking a constant 0.693 and dividing by k. Lowercase k is our rate law constant. Yes, go back to kinetics, it's the same thing. All radioactive decay follows first-order kinetics, and though I don't teach this in my Chemistry 1 class, if I take the the integral of the rate law for first order, I will get natural log of a particular mass of a substance that we'll call N equals the opposite of K times T plus the natural log of the amount of substance we had originally. So N is the amount after the elapsed time, K again is your rate law constant, T is your elapsed time, and N sub O is the amount originally. The units of radioactive decay can be plenty, but we're going to focus on two. One is the Curie. You write the unit with a lowercase, C-U-R-I-E, but the shorthand notation is a capital C, lowercase I. 1 Curie equals 3.7 times 10 to the 10th disintegrations per second. That means disintegrations of nuclei per second. So 3.7 times 10 to the 10th. Now do that. That's over 37 billion nuclei disintegrate per second for 1 Curie. It is approximated to be the activity of 1 gram of radium-226, by the way. It's what it's based upon. Another unit is the becquerel. Again, lowercase b, E-C-Q-U-E-R-E-L, and shorthand notation is uppercase B, lowercase q. It is the approved SI, or System International unit, and 1 becquerel equals 1 disintegration per second. There are 37 gigabecquerels in every 1 Curie. Units of radiation exposure are also plentiful. I'm going to focus upon the SI unit, which is the sievert. It can be equated with a gray. This is in some instances. A sievert is defined as the dose absorbed by specific tissue. A gray, G-R-A-Y, abbreviated as uppercase G, lowercase y, is the dose absorbed, but not necessarily by specific tissue. The sievert replaced the Röntgen equivalent to man, or REM, as a unit that was used for a number of years. If you've been exposed to 1 sievert, for example, you'll experience nausea. 2 to 5 sieverts, you experience hair loss and hemorrhage. Oftentimes 3 sieverts in an immediate dose, meaning not spread out over time, result in death in 50% of the people within 30 days. And if you've been exposed to 6 sieverts instantaneously, you're very unlikely to survive. Our typical background exposure per year, by the way, is 2.4 millisieverts per year. That's radiation from things like sunlight, from traveling in airplanes. Getting higher in the atmosphere gives more exposure to radiation. Having our dental x-rays once a year, that kind of stuff. It just really is minimal amount of radiation exposure for the typical person. However, someone who's going through, say, radiation therapy for a cancer might be exposed to 20 to 80 sieverts or grays within a several month period. And you understand why that person might experience nausea, hair loss, hemorrhaging, their red blood cell count goes down, that kind of stuff. So that explains hopefully some of what goes on in radiation therapy to you. Alrighty, let's look at a half-life problem. Practical application is using that fluorine-18 that's used in positron emission tomography. Its half-life is 2 hours. If you receive a dose of 200 millicuries at 8 a.m., how long would it take for 10 millicuries to remain in your body? At what time will you have 10 millicuries in you? That means you got to think about how a clock works. First thing I want you to do is solve for the value of K, your rate law constant. And in doing so, you'll use that half-life equation. Then I want you to plug into the linear equation that I gave you and solve for T, your elapsed time. And then you're going to have to think about the clock and actually figure it out. So, as I plug into my half-life reaction, I should be able to solve for K and find that K is 0.3465. The unit is reciprocal hours, or 1 over H. I then plug into my linear equation, and I will take the natural log of the amount that I will have after an elapsed time, which is 10 millicuries, equals the opposite of K, 0.3465 reciprocal hours, times T, plus the natural log of the amount I had originally, which was 200 millicuries. Now just be careful with those natural logs. Don't do too much rounding. 3 significant figures is what you should have. Even though I gave you 4 significant figures, I did so because that was a 5 at the end and I didn't really want to round all the way up to 0.347. As I solve for T, I should recognize that T's units will be hours. That is why you have the unit of reciprocal hours for K. Now, as I go through my motions of solving for T, I find that it is 8.65 hours after the initial dose of 200 millicuries that I would have 10 millicuries left in me. And that means if I got that original dose at 8 a.m., at 4:39 p.m., I'd have 10 millicuries left in me. Okay, and one last little concept is radioactive dating. So we don't just use radioactive isotopes to determine half-lives, to determine the amount of time it takes for something to go away, to act as medical tracers. I'm not even getting into stuff like nuclear reactors in this PowerPoint. There just is so much use for nuclear chemistry, kiddos. It is so much in your future. Just hold on to this knowledge. Last thing I'm going to discuss, though, is carbon-14. It's used to date substances that were once alive, because all of us that are alive are carbon-based units. we therefore will emit carbon-14 once we die, and the carbon-14 is a radioactive isotope. It's a beta emitter, and it has a half-life of 5,730 years. That tells us that it's not quite as dangerous as something, say, with a half-life of 2 hours. And as we use it to determine the age of carbon-based substances, we can take, say, a petrified piece of wood and determine how old it is. The Shroud of Turin, the drape in which Christ was laid, is said to be a certain number of years old based upon carbon-14 dating. So again, I have a little short movie in here that talks about dating a bone. Watch it if you will, enjoy it, and that's pretty much the end of my podcast and the end of another school year. I started these in February of 2008 with solutions, and I'm going to keep wrapping around. And in August, I'll get started with the new school year's podcast. So, gee, it's going to be stunning. I may have to redo the ones that I did in February and March because they probably are pretty bad compared to these new ones, huh? Okay, now you get your joke. Why are helium, curium, and barium known as the medical elements? Well, this one's a kicker, let me tell you. It's because if you can't helium or curium, you barium. Hope that left you with a tickle. Have a good summer. Enjoy, and I'll look forward to making more of these. Bye.